video covers section 6.4, and we went over the intro paragraph, so if you would like to read it yourself. Now I'm going to write down the definition of what is a polar equation and what is the graph of a polar equation, okay? So just copy it down word by word, please. So a polar equation is an equation whose variables are r and theta. And the graph of a polar equation is the set of all points whose polar coordinates satisfy the equation. Please copy that. Okay, so for example 1, we're going to graph a polar graph, and we're going to graph it on that polar grid, I guess, that we have on the right side. Now, we will be using the calculators in a minute. I'll show you how. But first, we're going to do one by hand, so you know where those numbers come from and why we have those points, okay? It's not that hard to substitute this one. So what we're going to do, like, for example, in rectangular coordinates, you're usually given the x, and then they ask you to find y, correct? And then you use the formula, you substitute x, if x is an independent variable, and then you find that. So in this case, theta will be our independent variable. And so we're going to be substituting the angle into here for this theta, all right? So the very first one will be r is equal to 4 times the cosine of 0. And so this will be 4 times, and remember, once you take the cosine of 0, you replace that with a number. And so that is 1. Very good. So the answer is 4. So for this one, the points I would need to graph will be r first, so 4, 0 for the angle. So it will be 0 degrees. We're somewhere here, right? But we're only going to plot a point, not the actual rate of the angle. And so we go to the 4th circle, because the radius is 4, so right there. So the next one, and so I'm going to kind of remind you of where cosine is. So right here, you already know the coordinates are 1, 0. Here at pi over 2, we have 0, 1. And then here we have negative 1, 0. And here we have 0, negative 1, right? So then we're going to be using the angles on the first and second quadrant, I think. So let's go ahead and write down what the cosines are. For example, we're going to need the one for pi over 6, and that one is going to be the square root of 3 over 2. And the one for pi over 4 is going to be square root of 2 over 2. And the one for pi over 3 is going to be 1/2. Okay, so we're going to be needing those numbers. So here we have r is equal to 4 times the cosine of pi over 6. Now, on the test, previous test you guys had, you had to substitute like this whole expression with the actual ratio, which is square root of 3 over 2. But some of you were still writing cosine and then the square root of 3 over 2. And then you were like, what do I do now? So that was a big mistake. So what you should do is, like, once you take this whole cosine of pi over 6, you get rid of the word cosine as well. So that would be the square root of 3 over 2. And here we can reduce the 4 divided by 2. That will give us 2. So this will be 2 square root of 3. So this point will become 2 square root of 3, pi over 6. And I forgot what the approximation was. So can someone please put it on the calculator? The 2 times square root of 3. I can't remember what it was.
3.46.
3.46. All right. So then it's going to be in between the circle with the radius 3 and radius 4. So the angle is pi over 6 right here. So between the third and fourth circle, so here's the third, so somewhere here. Okay, next one. The next one is going to be 4 times the cosine of pi over 3. And so the cosine of pi over 3 is right here, 1/2. So this will be 4 times 1/2, and that will equal to 2. So the point that we need to graph is 2 comma pi over 3. So let's find pi over 3, that's here, and then we need to point on the radius 2. There. Now here, I don't really know at this point. Well, let's keep going with the table. Next angle is pi over 2, so this will be r is equal to 4 times the cosine of pi over 2. Now, what is the cosine of pi over 2? You can see it here on my unit circle. 0. So 4 times 0 is 0. So we're going to graph 0, comma, and the angle is pi over 2. So that will be a point at the pole, which is like the origin in rectangular coordinates. Okay, so next one, let's go ahead and substitute. Now, 2 pi over 3 is located here. It's going to have the same coordinate as
Negative
this
2.
one, but negative. Very good. Carmel, is that you?
Yeah.
So, this will be 4 times negative 1/2. And so that will become
Negative 2 square root of
negative 2. No.
3. Wait, what? Just negative 2. Okay.
So then the point is 2, negative 2, comma, 2 pi over 3. So let's graph that. We find 2 pi over 3, that's here. And then if the radius was positive 2, the point will be here, right? But because it's negative, it gets reflected to here. All right. So we have one more, and then I'm going to add an extra one. So 2 more. 5 pi over 6. So this will be 4 times the cosine of 5 pi over 6. And so that one is the one with the square root of 3, negative actually, square root of 3 over 2. So that will be negative 2 square root of 3. So the point that we graph is negative 2 square root of 3, comma, 5 pi over 6. So the last one, you get negative 4 comma pi. So if we find the angle pi, and then fourth circle, 1, 2, 3, 4, but it's negative 4, so it's actually reflected here, and it will end up being here as well. And then the one that I skipped, I think it's like, it's actually square. All right, now that kind of looks like if we were to connect them, it will look like a hexagon, right? Like a regular polygon with 6 sides. However, I wouldn't know what's happening at the pi over 4, because that was not part of our table, but it doesn't mean that we cannot use it. So let's find that one. So at pi over 4, the radius will be 4 times the cosine of pi over 4. And so the cosine of pi over 4 is going to be the square root of 2 over 2. So then in this case, 4 divided by 2 will give us 2. So then we will get 2 times the square root of 2. And that is approximately 2.82. So we're going to have a point that will be, let's use the approximation, 2.82, comma, pi over 4. So we find pi over 4, and then 2.82 is like between the second and third circle, but kind of closer to the third circle, right? Because 0.82 is closer. So then that point is going to tell me that this is not a straight line. It's actually like an arc, a curve. So then I connect them here. right here, and then there should be another point here, right here. And so you should be seeing, because of the distortion of the projector, we're not seeing a perfect circle, but yes, on your paper you should be getting a perfect circle. Okay, and in reality, any graph that starts like that, that has in polar form and it has cosine theta, it's going to give you a circle. A circle that will be symmetric with respect to the what? Like if you fold it, where's it going to be symmetric?
Oh, the x-axis.
The x-axis, right? But in the polar world, we call it the pole. No, sorry, that's the origin. The polar axis. Very good. And so, yes, that is symmetric with respect to the polar axis. Now, since we had a 4 here, do you guys notice anything about the graph in the 4?
Yes.
What? Can you tell me? What relationship is that?
It's a circle. It doesn't forward.
Ends at 4. So if it starts at 0 and ends at 4, what is that line called?
The diameter.
Yes? The what?
The diameter.
Diameter. So yes, this number will give you the diameter. Okay, so if we look at your slide down here, we have another one that will also give us a circle, and that will be the one with sine. The difference is that that one will be symmetric with respect to the vertical axis. You guys see it? So it will be here. And also the constant that will determine the diameter of the circle. Alright? And so the project that you are going to do instead of the homework that you're going to do on Monday is going to involve, so you guys, who took Algebra 2 with me and we did that Desmos art project? So it's going to be kind of like that. We're going to do some stuff. But no abstract art. What?
And like we have to like put a picture or something too.
No.
I don't remember.
It's like a Christmas card.
Oh, I know. Oh, the tree?
That was another one. Okay, so let's move on. So when we were talking about functions that are graphed in the rectangular quadrant, we talk about 3 different types of symmetry. One is with respect to the x-axis, another one is y-axis, and another one is origin. And actually, let me correct myself. We do not talk about this one when we discuss functions. Because if we have a function, a graph that is symmetric with respect to the x-axis in rectangular form, then it wouldn't even be a function. Like a circle. But in the polar world, we do consider those 3. And so the first one, instead of calling it symmetry with respect to the x, we will call it symmetry with respect to the polar axis. And instead of y-axis symmetry, we call it with the line pi over 2, which is this line, the vertical line. Like in bearings, we used to call that line the north-south line. So think of it that way. And then, instead of calling it symmetry with respect to the origin, we will call it symmetry with respect to the pole. All right, so there are 3 steps, well, 3 cases, of course. So for the first one, this is for the polar axis. We replace theta with negative theta, and then we get something equivalent, and then it will be symmetric with that. Next one, we replace our theta with both of them with their opposites, negative and negative. Or if they were negative to start with, you change them to opposite sign positive. Then if we get an equivalent equation, then we say it's symmetric with respect to the line, or like the y-axis, the vertical line. And finally, with respect to the pole or origin, it will be if you replace r with negative r, and you get the equivalent equation. And remember, the polar axis symmetry is similar to an x-axis symmetry. All right. So let's go to the next slide. And we're going to graph the following. You guys will. So I'm actually going to give you the points so that we can make it go faster. Where's my phone? Oh, it's okay. So what I need you guys to graph, I'm going to give you the coordinates. So we're going to have 0, 0.13, 0.5, 1, 1.5, of 1.87, and 2. So I need you to graph those points. Okay, so now we're going to check for symmetry along the x-axis, which should be called the polar axis. Okay, and so for that, we're going to replace the angle, just the angle. So r equals 1 minus cosine, and then instead of theta as the original function, we use negative theta.
Whoa.
Now, this is easy because you should know that cosine, for example, if I ask you what is the cosine of positive pi over 4, you'll know it's square root of 2 over 2. What if I ask you what is the cosine of negative pi over 4? Is it the same?
Yes.
Yes, because cosines are positive here. So yeah, the cosine of a positive angle will be the same as the cosine of the opposite of that angle. And so when that happens, based on Fricka 1, when the function is exactly the same as the original, then we can say that it is even. Also, another reason you should know this is that when you graph the cosine function, it looks like that. Right?
Yes.
And isn't it symmetric with the y-axis? So that also tells me it is even. So the whole point of knowing odd even is so that you can comfortably know that that one is the same as the cosine of the positive angle. So what that tells me is that it's exactly the same as the original. And so because of that, I can just kind of copy the graph like that. So yes, we know Andrew's in love. Oops, did I say that out loud? Okay, so next graph. Isn't it cute?
Yes.
Isn't it cute? Okay, next one, we're going to practice how to test for symmetry, all 3 times, okay? So for polar axis, replace theta. Oh, it's already there. With negative theta. Then, we can't just do that like what we did with cosine because sine is not even. It's the other one. What's the other one?
Fine.
Odd. Odd. So, for odd functions, like for example, the sine of pi over 4, which will be like here, it will be positive, right? But the sine of negative pi over 4, if we go in this direction, is going to be negative. It will still be the same number. So it's like the opposite of what the sine of negative pi over 4 is. So then what we do here is, after we do this change, since sine is odd, it's going to change the sign to negative sine of positive theta. by following this notion. And breakout one, we just talk about it this way. Like if you put a negative here, then you get the opposite of positive. I go, oops, we'll call that. Yep. Let's see. Okay. The opposite of FOS. Like that. So that's why I have a negative here, guys. So then this will be 1 minus 2 sine of theta. So if we compare it to the original function here, it's not the same. So there's no symmetry with respect to the polar. Now let's check for symmetry with respect to both, to the vertical line pi over 2, or like the y-axis. So here we already replaced r with negative r and theta with negative theta. So what we will have to do is multiply both sides of the equation by -1. Okay, but first I'm going to take care of this part before I multiply by -1. Actually, let me just do that first. So it will be negative r is equal to 1 minus 2 sine of theta. Why did I do a minus? Same reason here. Because we replace the angle with negative theta, and sine is an odd function. After that, we multiply everything by -1. So this negative r turns to positive r. The positive 1 turns to -1. And the -2 turns to positive 2. Yeah. So now, do we compare it when we compare it to the original? Is it exactly the same? No, almost, but not really, because the constant. So we say no symmetry. Now the last one is pretty simple. We just replace r with -r, but because we want to find out what r is, we multiply everything by -1. So that will be positive r is equal to -1 minus 2 sine theta. So it's pretty obvious that it's not the same as the original, right? So we'll say no symmetry with respect to the whole. Okay, now I'm going to give you the points, the coordinates of the points, so that you guys can graph it. Yeah. Okay, so I'm just going to put a comma. Come on. 1, 2, 2.73. And here we have 2.73. Okay, so those are the coordinates. I'm going to give you some time to graph it. It's very simple. Actually, I'm going to start graphing lines. Are you guys getting the same graph almost? Yeah. So it's gonna have a little loop inside. And then just you guys see how it goes back to 0, so then we go back there. And then the last point is going to take us back to here, because it's 2 pi, and the radius is 1 to 0. Like that. So, what is it? I know that when we tested geometrically, algebraically for symmetry, we got no symmetry, right? At all. And we did it right, because I actually checked the book, and there's a paragraph that tells us that sometimes, even though algebraically it will say no symmetry, the graph could still be symmetric. So if you have to pick one for symmetry, what would you say? Which one will be the one that it is symmetric with respect to? With the line pi over 2. Very good. The one that in the rectangular coordinates we call the y-axis, right? So if we were to fold it along this axis, we will have the same. Even though algebraically, don't ask me why, because the book doesn't even explain why. It just happens. Okay. So for those graphs, remember when you just have like this little part or this little part, you get circles, right? So when you add a constant to them, like right here, you're gonna get those type of they look like hearts, or they look like little spirals, or little snails, whatever you want to call them. And so they have this French word that it means snail. Snail. It is pronounced song. Okay, and it's kind of weird, but the ratio of those constants, like the one you're adding and the one you're multiplying, the trigonometric expression, is gonna determine the shape. So for example, if that ratio is less than 1, you'll have one with an inner loop, like that. If your ratio is equal to 1, you'll have one that looks like a heart. And they're called cardioids. And in fact, some devices the doctors use, they rely heavily on those shapes. There's actually some picture on the book. I'll show it to you guys next week. Also here, you can have it almost looks like a circle, but it has a dimple. And then this one is just more like a circle or like an ellipse, you could call it.
Does it have like a small,
This one has no dimple. It looks like it, but it might be the projector. It looks straight? Yeah, it looks. Oh. Okay, so let's check for symmetry on this one quickly. And then I want you to graph it on your calculator. So let's first check for symmetry. So the step is already done for us there. So this is going to be 4 times the negative sign of 2 theta. So that will be negative 4 sine of 2 theta. So no symmetry, right? The next one we change both. So this will be negative r, and then we're going to have 4 times the negative sine of theta, of 2 theta. So then this will turn into negative 4 sine of 2 theta. And if we multiply everything by negative 1, they're going to change to their opposite sign. So we'll have positive r, and then positive sine 2 theta. So then, yes, we are going to have symmetry with respect to that vertical line pi over 2. Let's check the third one. And so that one says, well, we're just going to multiply everything by negative 1. So we'll get positive r is equal to negative 4 sine of 2 theta. All right. And let's graph it. Let me see if we have some. Go ahead and graph it on your calculator while I write the coordinates. Just type it in your calculator. So in case you don't remember how you need to go to the graphing part. So if you're at home, also make sure that your calculator is in radians. So go to settings, document settings. And then we want to make sure that our angle is in radians, okay? After you do that, press make default, like that. Then we go back to graph, press tab, and if it's not in polar form, go to menu, then graph entry, and then polar. Okay, and then for that part, so we're going to enter 4 sine of 2, and then theta. And it's an yes, it looks like a butterfly or a flower with 4 petals. What can you guys tell me about the length of a petal? Yeah, of one single petal. How long is it?
Two.
It's actually 4. And if we had the whole like circly thing, you could see. 1, 2, 3, 4. So we'll go like that. But then let's try and change something from the equation. So if you just double click, you can go back here. Let's change that 4 and make it a
6.
Letters. Control C.
Make it whatever you want. 6, 2, 3, 5. You try your own number. See if they shrink or elongate.
Oh. Oh, yeah.
And this is the most beautiful graphs you ever seen. So see, I put a 5, it went a little longer. Now I want you guys to try something.
What if we put it negative?
Ooh, try it. Wow, nice. So that's kind of like what we're going to do on Monday. Yeah. They're beautiful. And so that's what you got, kind of like the art project that you're going to do on Monday, okay? It's going to be very entertaining. Okay, so let's just to finish this quickly. This is the relationship. So we graph something like this one, right? So the length of the petal is determined by this constant. Now, the fact that it has 2 theta, it makes it have 4 petals. Go back, petals. Go back to your graph and put a 5 there instead of a 2. Put a 5.
It's gonna look like that.
Oh, true.
Yeah.
Okay, so to summarize, for those 2, if the number is odd, it's just going to have the same amount of petals. But if the number is, this number that goes with theta is even, is going to have twice the amount of petals, right? Then, of course, there's another rows that we get with cosine. So with cosine, it also repeats. If you put an even number, it will double the number of the petals. But if you put a odd number as a coefficient of theta, it's going to give you the same number of thetas. And then the last slide, we don't need to worry about that one. It's just going to give you some other shapes like this one.
What if you put like square root?
So they're like the infinity sign. Well, that's what I want you guys to experiment with on Monday. Because you could also do some that look like fireworks. Instead of having like curvy petals, they could be like things like that. Okay, so yeah. All right, so this is the end.